Hi everybody, welcome to our second lecture on Markov Chains and Processes. Today we're going to be going over preliminary information, or sort of the basics of probability that for most of you will probably be familiar, and if not, you can dig into the textbooks that we've suggested to you and kind of fill in some of the holes that you might be missing. We'll spend this lecture and the next lecture on the preliminaries chapter of the notes. We'll finish that chapter in the next lecture, and we'll start in on chapter 2. But so this is mostly expected to be review. And the pace that we'll give it in, that we'll deliver the material in today, is sort of unnatural from the standpoint of learning this stuff for the first time. So you should be aware of that. So if some of this material is stuff that's new to you, it is going to be coming out faster than would be comfortable. And so you should be prepared for restudying it and getting it at a more reasonable pace for yourself. But so we're just going to introduce all the sort of basic preliminaries that we need for the rest of the module. So I want to just start off by introducing a lot of fundamental terms. So first I want you to consider some sort of an experiment in the mathematical sense. So consider an experiment. And what we mean by that is there's a variety of different ways to kind of interpret this, but you can sort of think of this as meaning an observation of a random variable. All right, so that's the experiment you want to consider. Suppose you have something like, for example, the outcome of rolling a pair of dice, or some other similarly only probabilistically knowable thing, not deterministic in nature. So we're going to describe the sample space. We'll call this capital S. So this is the sample space. And this is the set of all possible outcomes for the experiment. So this is all possible outcomes. And we'll say that a subset of this sample space is called an event. So I'm going to call that A. So A is a subset of S. This is called an event. And this is maybe a little bit already kind of troubling notation. I'll tell you why. So the next thing I want to introduce is the probability of the event occurring. So this should all be relatively familiar. So this is the symbol for probability. So the probability of A, so how you read this, is equal to, and so I'm just going to write how you read it, probability of A or in other words, this is the probability that the outcome is an element of A. The outcome of the experiment is an element of A. Right, so the reason I say this notation is already a little bit, or these definitions are a little bit clumsy, is that the subset, the sample space and the subset are linked to this particular experiment, or some say random variable. And we'll see in a minute why this sort of complicates a little bit the way you would interpret these definitions, because what we really mean by this probability of A is it's the probability that the outcome of this specific experiment is an element of A. So it's a little vague in that it doesn't actually reference the specific experiment you're talking about, which isn't so important except when you're talking about lots of different random variables, which is going to happen. So that will come up. So we'll end up having to kind of augment the notation a little bit, and you'll see that today. Okay, and so we want to, so this is the notation for probability, but the way we introduce probability formally is just through a set of axioms. So this is the notation for what a probability is. But what are the axioms that define probability? So there's 3 of them. So probability axioms. And with these, you can build up all of the rules for probability, and we won't do that, but we'll talk about a little. Well, maybe we'll do kind of a little bit. The first, so there's 3 of them again. So the first one is that the probability of A. Normally we don't really say this bit, but we'll say it's a real number. So this is sort of addition to the axiom. And the probability of A is greater than 0. Or equal to, greater than or equal to 0. Right? So that's the first axiom. The second axiom is that the probability of the total sample space. So if you made the event A is a subset of the sample space. So if you make the entire sample space your event, then the probability that your outcome is in the space of all possible outcomes, this is 1. So that's an axiom. And then the third axiom is a little more complicated. The third one says that if you've got several different events, and so I'll just write them with an index A1, A2, and so on. And if they're what we call mutually exclusive, or the simpler term, the shorter term is disjoint. And of course, what we mean by this disjoint means that if I is not equal to j, then it implies that the intersection of ai and aj is 0, or rather is the empty set. Right, so there's no common elements between 2 disjoint sets. And so for a collection of sets to be disjoint, this means what I've written down here. And so the axiom, so this is axiom number 3. So this is just the setup. If you have these disjoint sets, A1, 2, and so on, then the following thing is the axiom. Then the following thing is true. We say that the probability of the union of all of those things, so say I equals 1 to infinity of all the A's, AI's, this is equal to the sum of all of the individual probabilities. So those are the 3 axioms that we use to define probability, so these 3 things. And from these we should be able to build up all sorts of different rules for what qualifies as a probability. Okay, so let's look at some of these things. So we're going to build rules from these axioms. From the axioms 1 to 3. Okay, so let's try one. So we're going to say the following thing. We're going to say, let's suppose, so let x, capital X, this is what my capital X looks like. Let's suppose that capital X is a discrete random variable. So I'll write that as drv. Suppose that x is a discrete random variable in such a way that it only has possible values that are integers 0 or higher. So I'll just write that as with values. So what this means is with possible values. 0, 1, 2, and so on. So any integer that's 0 or larger. Then the following, this is just a definition. So the following collection of rules. So the collection of rules that we write like this, the probability that x is equal to n is written as p with a subscript of n. So that's just a notational thing. These things are collectively called the probability mass function. And the word mass appears here. It's sort of a little bit of a theft from physics. We use the word mass here in contrast to using the word density later. And density is a density in the sense that if you multiply it by some other quantity, you get a mass. And so this is the probability mass function. It's the probability that x, it's the collection of rules, the probability that x is equal to n. And now here you can already see a little bit of a small problem with our notation here. So we have in the parentheses we've written not a set, right? X equals n is not a set. It should just be n, but it's implied that we're talking about the random variable x. And so what we'll often do when there's more than one random variable, which there soon will be, is we won't just write the elements of the sample space that make up the event, but we'll say which random variable has to be equal to those elements to try to make sure that there's no ambiguity here. Okay, and so these quantities make up the probability mass function, which we'll use a lot, and so this is PMF. We'll say that a lot. And so then the axioms give the following. Somewhat famous rules. Right, so first they give the rule that each of these p's has to be between 0 and 1. Right? Now that's partially implied up above, that probabilities have to be, what did we say, have to be positive? It's the fact that the subspace, or that the sample space has to have a probability of 1 that gives us this upper limit, which is one of the axioms. And then the other thing that we get, so sometimes this is called like positivity, but I think I use that word more than most people, so you might not find it called that by many people, but I call it that sometimes. So maybe you call it the positivity condition, or sorry, it's not positivity, right? It's positivity was the axiom, so let me take that out. It's 0 and 1-ativity, if you want. But it's a sort of a condition on the PMF. And the other condition that we use quite a lot is the so-called honesty condition, which says that all of the PMF, all the p sub n's have to add up to 1. And this is called the honesty condition. We named this one because we use it quite a lot. And so these are things that are required because of the axioms, and you can prove that, but we won't prove this. And so now let's look at the following things. Let's suppose we have two different events, A and B. We say that these things are independent if the following is true. So the probability of their combination the intersection A intersection with B is given by the product of the two probabilities. If that's true, we say that these two events are independent, right? Now, if we have random variables, so let's say x and y, we say that those are independent if the following is true. And so we're going to immediately run into this issue of the notation that I was describing. So if for any events Now here I'm sort of remaking what is an event. So we say, here's one event. X is an element of some set little d, lowercase d. So above we would call the set lowercase d the event, but we have to be a little specific, make sure we know which experiment or random variable we're actually talking about. So if that's one event and then another event is this experiment, observe y, and you find that y is an element of some other set e, and so this is again kind of like a little bit of a sloppy transformation of our notation. Then we say that the random variables x and y are independent if the following thing is true, and that is we write it like this. So we say the probability that x is in D intersect, so and y is in E, oops, is equal to the probability that, oh, I don't need that anymore, the product of the two different probabilities. Well, which looks just like what we saw above, except this one is phrased in terms of random variables rather than different events. And so I'll just highlight these things. Maybe I won't, that's big enough, I think. So we'll say events A and B are independent if the following is true. Random variables X and Y are independent if the following is true. So those are pretty closely related statements. Okay, so now let's make a little definition. Right, so we're going to define conditional probability. So conditional probability is something that's defined between multiple events. So we'll say that, let's suppose we have two different events, and we'll call them A and B, in such a way that B is not impossible. So we'll say that we'll say that for events A and B, such that the probability of B is not 0. So in other words, we're sure that B could actually happen. Then we define the conditional probability and really what we're defining is the probability of A conditioned on B. So we'll write that at A conditioned on B. So that's what we're really defining here, but you often just use this as a definition of conditional probability generically. So we say this is the probability of A, and then we write a vertical bar here, B. And we'll write how you say that in a second, but we write this as, the definition of this is the probability of A intersection with B divided by the probability of B. Right, so that's the definition of the probability of A conditioned on B. Right, so that's a conditional probability. And we read this in the following way. So this should be quite familiar to you. You read this in the following way. You say that that symbol up there, probability of A bar B, you read this as probability, sorry about that, of A given B. Right, that's how you read that. That should be quite familiar. And we write, the other thing that this sort of is we're going to introduce is we read the probability of the intersection of A and B. Sometimes we just write this like this, the probability of A comma B, because again, we often get kind of fast and loose with sets versus some sort of like random variables equal to a set. So we say this is the probability of A and B. All right. Yeah, so that's conditional probability. Now, a fun kind of exercise is, so you should be able to do the following. You should be able to use Venn diagrams. Sorry about that. You should be able to use Venn diagrams. Is there two N's in Venn? Oh, I don't even know. Use Venn diagrams to convince yourself that this is a sensible definition, or some other tool, whatever works best for you, to justify this interpretation. All right, so this is just the definition of the conditional probability, the ratio of the probability of A and B to the probability of B. But you should maybe play around. I think it's fun to play around with some Venn diagrams or some other such thing to convince yourself that this actually makes sense, that this is the same thing as the probability of A happening given that B happened, or something like that. So you should try to kind of put this into, I don't know, more simple terminology to make sure you believe that this interpretation makes sense. Okay, so now we're going to introduce a few theorems. So we're going to introduce, we'll do some theorems and proofs and so on. We won't do a whole lot of proofs today. But this is a famous theorem, so I'll give it a name. I won't try to name the theorems with the same numbers that you see in the notes, because potentially those could change. But this is such a famous theorem that we'll give it a name. It's called the theorem of total probability. Right, so the theorem of total probability looks like this. We say, suppose you have some events that cover the sample space. That's one way to say it. So we'll write it like this. Suppose you have the collective union of all these different events, so BI. Suppose that's equal to the sample space. And it covers it in such a way that they're disjoint, so they don't have any common elements. So B1, B2, and so on are disjoint. Right? And then here's the theorem. We say that the probability, so this is a requirement for the theorem, the probability of A is equal to this series. So sum over n equals 1 to infinity of the conditional probabilities A given B sub n times the probability of B sub n. Okay, so that's the theorem there. We should be able to prove that. It's relatively straightforward. Okay, so we'll do our little proof here. And this is probably familiar to you, but that's okay. It's good to do the exercise. So we'll write the probability of A. This is the same thing as the probability of the intersection between A and S, right? Because A is a subset of the sample space, and so the intersection of A with S is A, right? So that's fine. And then we say this is equal to the probability, and we put in this fact that the B's cover that. So we say this is the probability of A intersection with the union, oops, the union of all the B's. So I'll just write a subscript there and not write the boundaries. Right, so we'll write that. And then this thing, we're gonna distribute that intersection. And so this is the probability of the union overall. So this is summed over all the n's of A intersection with Bn. Right, so this is just the distributive property of sets. And this guy is equal to then a sum. Oops. So leave a little space here. So let me just pause before I write it down. So what's happening here is we have a probability of a union of a bunch of different events. Each one is A intersected with B. But if the B's are disjoint, they don't share any common elements, then all those intersections are also disjoint. And so we can apply that axiom. Was it axiom 3, I think? So we say this means the sum probability of A intersection Bn, right? So this is by axiom 3. All right, and then if this is the probability of A intersection Bn, we make use of the definition of the total probability theorem to rewrite that as, or sorry, not the total probability theorem, the definition of conditional probability. The total probability theorem is what we're proving. Probability of A given Bn times the probability Bn. And that's the end of the proof. Okay. Let's look at another theorem that we won't prove here, but we'll state it. So I'll just write that for short for theorem. And this one is called, this one also has a name, it's called the total conditional probability theorem. And it works in a similar way. So we're going to start off with the same supposition. So I'll just steal it. So we'll copy this guy. This bit is exactly the same. So we'll suppose that the B's cover S and are disjoint, right? Then we'll say that for any two events A and C, A and C in such a way that C is not impossible. Right, so it's greater. You could just write it as greater than 0. That's fine because it can never be less than. So as long as that's true, as long as C is not impossible, then we can say the following things. I'll just write this out. It's a similar statement. Probability of A given C is equal to the following. So it's a sum over n of the probability of A given Bn and C. Right? So that's the union of B and C there, Bn and C, times the probability of Bn given C. Okay, that's the theorem of total conditional probability, or the total conditional probability theorem. And we won't prove that today, but you'll prove it on your tutorial sheet. It's the very first question. So proof number 1 on tutorial 1. Right, so that's your first question on the tutorial. All right, so now let's introduce some more definitions. Again, this stuff should be review. If it feels like it's coming too fast, that's the reason. It's meant to be review. Okay, so we're going to define a generating function. So we'll say that, let's suppose you have some sequence. Just any sequence. So A0, A1, A2, and 3, and so on. Let's suppose these are all real numbers. Right? Then the corresponding generating function It's just something we build out of that sequence, and we name it, so the generating function, G, with a little bar on the edge of the G of S, where S is anything at this point, is the following. It's just a definition. G of S is equal to the sum, and going from 0 to infinity, of S to the n times A sub n. And we don't really say anything about what S is, but you can certainly see all sorts of troubles if you put in funny things for S, such as S bigger than 1. That would be kind of problematic. This thing would diverge. But that isn't really our concern. You can get all kinds of interesting, weird stuff if you put in funny values of S, but that's not our concern for the definition. Okay, so that's just called the generating function. And we're going to not really use this so much, but we will make more use of the probability generating function. And it's the same, but for the sequence being replaced by a PMF, right? So let's suppose, and we'll phrase it in terms of a random variable. So let's suppose you have, so for some discrete random variable, x, with values 0, 1, 2, and so on, and a given PMF, P sub m. Oh, I guess I use n. Is that what I've been using? All right, so P sub n is, again, this is the probability that x is equal to n. Right? So this, then the following thing is called the probability generating function. Probability generating function, PGF, is the following. So we write it as the same kind of thing, G, but we'll put a subscript of X underneath it because we know that these probabilities came from a particular random variable, say as a function of S, and this thing is equal to the same expression with the A's replaced by the P's. N equals 0 to infinity, S to the n, P sub n. Okay, so that's just the definition of the probability generating function. Maybe we should highlight that. And then up here, this is the definition of the generating function, just a generic generating function. All right, so these things, the probability generating function, I think it's always the sort of thing that when students encounter it for the first time, or even the second or third or whatever, it's a little bit of a weird thing. It's like, why are we introducing this bizarro thing? And if you've seen it before, as I expect that you have, it's familiar kind of what sort of things you can do with it, but it sort of is a good reminder just to point out the following thing. So notice, or note, you should just view this as a transformation. View the probability generating function as some sort of a transformation of the PMF. Or sometimes in math we say transform, as some sort of a transform of the PMF. In other words, it's just like sort of something to do, something fun, something to do with the different with the PNs. Or maybe a better way to say it is a way to change your point of view. Right? So you use it in problems that you're trying to solve that are giving you trouble, and you can just think of this as like a change in perspective. And it certainly is the case that there's problems that you'll encounter which, if you try to solve them in the sort of what might seem like the obvious straightforward way, it gets challenging. And if you instead say like, oh, what if I just restate this thing I was trying to do in terms of the probability generating function? You may find that suddenly things get a lot easier. And so it's worth pointing out the following thing. So the PGF is in fact something that some people call a one-sided Z transform. You don't really need to know this. It's just sort of interesting, I think. One-sided Z transform. That's, I think, probably not familiar to most of you, at least that name. Maybe it is familiar to you guys. I'm not really so sure. But there's this other thing that you guys will encounter, or have encountered, I think, the moment generating function. And that is a more familiar transform. So that's the Laplace transform. And another one, which I don't know if you've used, but we call it the characteristic function. And this is the Fourier transform. And I only want to write this down because depending on your background, you may know these things, or maybe even just one of them, as, oh yeah, the first time I saw Laplace transforms, I didn't know what they were. They were just this weird thing. Oh, but then we were able to like solve differential equations by doing that, by transforming a bunch of stuff, and it turned out to be really powerful, similar with Fourier transform. So it's good to keep in mind kind of what's happening here. We introduced this probability generating function for a similar purpose, that some problems are just better solved when you kind of switch to this other universe, this other basis, or this other perspective of the probability generating function. So that's why we introduce it. I always feel like it feels a little bit forced, or like what's going on here. Okay, we're going to do an example and a couple more theorems. So here's our little example. Oops. Let's suppose you have a random variable that is Poisson distributed. So let x be Poisson distributed with parameter lambda. This is probably a problem you've done before, but I want you to calculate or find the probability generating function. Right? That's meant to be a lowercase s. It's not supposed to be the, hope that was clear. It's not supposed to be the sample space. Not much better, but so compute, so find doesn't mean Google. Compute the probability generating function. Okay, so this is something you probably have done. Maybe you have forgotten it. So let's just go through it. The first thing to do is to know what is the probability mass function. So the probability mass function is the following. This again, you should also know. P sub n is equal to lambda to the power n e to the minus lambda divided by n factorial. Right? So that's the probability mass function. And with that, we can just straight ahead just plow through and compute the thing. So, okay, so the probability generating function, according to the definition then, is given by this. So we say it's the sum n equals 0 to infinity of s to the n, and then this whole quantity, I'm going to put it here, right? That's p sub n, right? And now we just rearrange this sum. So the first thing to notice is that e to the minus lambda doesn't have an n on it, right? So we have e to the minus lambda sum over n, and then what do we have? So we have s times lambda to the n over n factorial, and this is n equals 0 to infinity, and that should look familiar, right? So normally I would pause if it doesn't look familiar, so you should pause and see what you think this is. So that's an exponential. It's the Taylor series. of e to the s lambda. And there we've got the probability generating function. So it's e to the lambda times s minus 1. And that's a sort of famous result. Okay, and I think it's one you probably, most of you would have actually already computed. All right, now let's look at a little theorem. This is an important theorem, but it's not one we're going to prove. It's about uniqueness. We will use it, but we're not going to prove it. So let's suppose that x and y are discrete random variables. With values 0, 1, 2, and so on. And then we'll say, suppose that they have the same probability generating function. For every s that you can think of. Well, not every s, actually. You should be able to think, why would it be a problem to say for every s? What's a little weird about that? If you remember, right, the probability generating function, or generating functions in general, they have trouble with certain values of s. They might blow up or something. And so we'll say, if this is true for all sort of sane values of s, or all s's with absolute value less than 1, then they have the same PMF. And I can't write p sub n anymore because now I've got two random variables, right? So I say probability that x is equal to n is the same thing as the probability that y is equal to n. Doesn't mean they're the same random variables, right? It just means they have the same PMFs. Okay, and I won't prove this, so proof omitted. Okay, let's try a little example kind of going the other way. All right, so let's suppose that we've been given a probability generating function and I want to compute the PMF, right? These examples are a little funny because they illustrate something you can do with probability generating functions, but they aren't really kind of the purpose. Again, the purpose is this change of perspective. So let's suppose you've got this probability generating function. And it looks as follows. P times little s times 1 minus q times little s all to the minus 1. And p times q is equal, or sorry, p plus q is equal to 1. So suppose this is true. Then what I want you to do is find the PMF p sub n, right? That's not to be confused. That p has nothing to do, at least not explicitly, with that little p up there. Okay, so this should be something I think you've also done this. Well, maybe you haven't done this exact one, but it's straightforward. So we'll do it. Probability generating function of s looks like this. So this one's a little less straightforward, I should say. So I'm going to write this out, p times s. And let's go back here and think about the definition here. Where is it? Somewhere up here, way up here. Right, so the probability generating function looks like this. And so it's some sort of a series in terms of powers of s, right? And then the probability mass function are the coefficients of that series. And I want to find the probability mass function. And so what I want to do is I want to take this quantity here and write it as a power series in s, right? And so the ps term, this bit here, I just leave out in front for now. And I just write out the expansion of 1 minus qs to the minus 1. So famous expansion. Okay, so we've got 1. And then the way I always do this, I always take this guy, multiply it by that. And so I get plus q times s. And if this were a physics class, I'd be kind of done, probably. I'd say, like, oh, that's a good enough approximation. But anyways, you keep on going, right? It's a famous series. Plus qs squared plus qs cubed, and so on. And now if I were to distribute the p times s, I just get ps plus pq s squared plus p q squared s cubed plus p I've made a mistake here, right? This 3 is meant to be out here. All right, so I get sorry, got a little distracted there. P times q cubed times s to the 4th, and so on. And from that, I can read off the probability mass function, right? Because look, I want to look at powers of s. There's a power of s. There's the next one. There's the next one. And there's the next one, and so on. And so if you look at this long enough, you should be able to see p sub n. And if you don't see it, pause and check, is equal to p q to the n minus 1. Right? So if you don't see it, just write those out and then you'll see the pattern. Okay, and that should look familiar to you, I think. I think it should. I think I might have taught it to some of you. And so this is a famous PMF. So this is a PMF for a geometric distribution. Right, so that's a famous thing. Okay, we're going to just introduce one more definition here for today, and then we'll write out a proposition that we won't prove. We'll be done. Okay, and again, this is all mostly review, I hope. But if not, read the references and kind of prepare yourself. Okay, so let's suppose you have some random variable x. We'll stick with discrete ones for now. So for x, a discrete random variable with some known PMF, right? Then we make the following definition. We say that the expected value of some function f of the random variable is the following. Oh, and we write it. Sometimes you call this expectation value. I'll switch back and forth between those two words. So maybe I should write it down this first time. Or expectation value. Worth reminding yourself, because I'll probably switch around with that a bunch. The expected value or the expectation value of f is the following. So we write it like this. Expected value of f of x, capital X there. So that's E with a little bar next to it again. This is equal to the sum, n equals 0 to infinity of f of n p sub n, like that. Oh, I think I need to put in here with values 0, 1, 2, and PMF looking like that. So that's the definition of the expected value of some function of the random variable x. And again, that should be a sort of familiar expression. Okay, we're going to finish off with a proposition here, and that'll be the last thing for today. So this is a proposition, it has 3 parts, and we're not going to prove it here, but I think it's on your proof sheet, so you can go through it if you haven't, or if you want a review of it. So first we say the probability generating function. So normally you should preface this all with, like, you know, suppose x is a random variable, blah, blah, blah. Okay, so we'll say that the probability generating function of x evaluated at 1 is equal to 1, right? The fact that there's a 1 on the right-hand side here should give you a hint about what you have to use to show it. Again, you've probably done it before, so that's the first part of this proposition. The second part says that the derivative with respect to s of the probability generating function, or a probability generating function, evaluated at s equals 1. So that's a really long, fully detailed way to just write out what normally people write as like g prime of 1. This is the expected value of x. So that should be quite familiar, I think. And then the third part is that the second derivative, so this notation here, I'm not going to rewrite that over and over again. So the third part says that the second derivative evaluated at 1 is equal to this funny expression. So it's the expected value of x squared minus the expected value of x. Okay, and that's pretty much all I want to do today. So again, this is a proof. This is proved. So this is proved. Proofed? It's proofed. The proof of this is on your sheet. And you've probably proved it before. So it's probably review. Okay, so that's all I want to say for today. I hope everything is going all right and you have lots of resources. And I will talk to you next time. Bye.